APAC session of our KubeFleet community meeting. And as mentioned on the agenda, we'll be doing a presentation to introduce KubeFleet's capabilities, its performance, and its performance and scalability target. Hopefully, this can help Luke and any viewers in the future to understand KubeFleet better. So I'm Michael. I'm a contributor to the KubeFleet project, and I work for Microsoft. Let's just jump right in. So about KubeFleet. KubeFleet is a CNCF sandbox project that enables developers, operators, and admins to easily and effectively manage their Kubernetes clusters and the multi-cluster workloads. The whole project was donated to CNCF on January 2025, which is roughly 1.5 years ago, I guess. You can find our source code on GitHub. We also have a website, KubeFleet.dive, which features our documentation. So KubeFleet is a part of a long journey to enable a multi-cluster experience in the Kubernetes ecosystem. And this journey actually began a long while ago. When Kubernetes first started, that was Kubernetes 1.10 really. The community back then already came up with the idea of enabling a Kubernetes multi-cluster experience. And the community as a whole came up with a project called KubeFed, Kubernetes Federation. But back then, Kubernetes was still young, and the API, many APIs we know about today, hadn't matured yet. So eventually, the KubeFed project was kind of stuck in a very weird place where it doesn't really feature great support for many of the new, more developed Kubernetes APIs, and as a result, the project was later abandoned. But the journey didn't stop there. So the Kubernetes community gave the idea of federation another try, which eventually became the project we know today as KubeFed v2. And when the KubeFed v2 project first started, it received a lot of attention and was quite popular. But eventually, the popularity died down, and roughly 3 years ago or 4 years ago, the Kubernetes community, the multi-cluster seek to be more specific, decided to archive the project. And since then, there hasn't really been a community coordinated effort to enable Kubernetes multi-cluster experience. Instead, different organizations began their own exploration into this problem domain. We have Kamada, which was originally developed within Huawei. We have OCM, Open Cluster Management, which is a collaboration between Red Hat and Alibaba. And we also have KubeFleet, which comes from Microsoft. So we all try to approach this multi-cluster problem, and we all come up with solutions in different flavors. You might feel that this is we are competitors in this ecosystem, but there's more in this relationship. All those projects, we understand that different organizations do multi-clusters differently. And there's really not one universal solution to the multi-cluster problem. So we all come up with our own solutions, and we all understand that there's definitely value to standardize some of the common APIs in the multi-cluster ecosystem. So there's actually close collaboration between the three projects. We all attend multi-cluster SIG meetings regularly. We have joined work groups to propose standardized APIs to the community. So yeah, we are competitors, and we are also collaborators in this domain. And in the past few years, we also see more and more different applications come up with a multi-cluster support. We have Argo CD, we have Flux, we have Q. They all support multi-cluster to one degree or another. So that's a situation we are in right now. And coming back to KubeFleet, so as I mentioned, we are a multi-cluster management platform project, and at the core of our solution sits this hubs and spoke architecture, which is also actually this pattern was also adopted in Kamada and OCM as well. So specifically in this architecture, every KubeFleet deployment comes with one hub cluster and a number of member clusters. On the hub cluster, we run a special deployment called KubeFleet Hub Agent, which reconciles all kinds of KubeFleet API objects. The hub cluster essentially serves as a portal for management, kind of like a focus point where you can view all the member clusters and you can orchestrate workloads among the member clusters. And on the member cluster side, we also on each member cluster we also run a deployment called KubeFleet Member Agent. What this agent does is that it will listen to the changes and requests on the KubeFleet Hub cluster, and then it will perform some operations. Most commonly apply Kubernetes resources to the member cluster side. The interesting part about this architecture is that in this system, in a Kubernetes deployment, we do not assume that the hub cluster can actually connect to the member clusters. In some deployments, it's not possible at all. Instead, it is a member cluster who's trying to making the connection to the hub cluster. We believe this is setup that enables better security and better flexibility in our deployments. So now, aside from this hubs and spoke architecture, we also provide APIs in three problem domains. Those are the domains we think that matters most in the multi-cluster ecosystem. We have the placement APIs, which is responsible for orchestrating workloads from the hub cluster to all member clusters. We have a rollout API, which is designed to help you safely roll out changes to the member clusters, kind of similar to a CI/CD pipeline. And we also have a cluster management API, which helps you to observe, which helps users to observe their member clusters and gain insights on the system. So that's the general idea. And going on, okay. Yeah, so here on the screen, we show an example of a Kubernetes placement API. As I mentioned, what this API does is that it orchestrates workloads so that they can be placed from the hub cluster to the member cluster. The API consists of three separate parts. The first one being the resource selectors. It basically tells Kubernetes what resources to place onto the member clusters. In this example, you can see it selects a namespace called work v1. When Kubernetes sees this resource selector, we'll try to find the work v1 namespace on the hub cluster, retrieve the YAML for this namespace, and then we'll try to place this YAML to all the member clusters. The second part of this API is called a scheduling policy, which basically tells Kubernetes where to place the resources, or more specifically, which clusters to place the resources. Kubernetes features a really rich and flexible scheduling experience. This example has a simpler end. You can see on the screen that it uses a peak all placement type, which basically tells Kubernetes to place the namespace to all the member clusters. But you can do much more with a Kubernetes. You can select clusters based on a label selector. You can tell Kubernetes to pick clusters that has the cheapest CPU cost or has the cheapest memory cost. You can also tell Kubernetes to favor clusters that has say the lowest node count or has the most available CPU or memory. All those kind of situations are all acceptable to KubeFleet. And the last part of the placement API is called the strategy. It basically tells KubeFleet how to roll out changes to the member clusters, which we'll introduce in a later section. So we have two separate placement APIs, one called cluster resource placement and the other called resource placement. As their names imply, cluster resource placements are used to handle cluster scoped resources, and resource placements are used to handle namespace scoped resources. We added those two separate variants to better support multi-tenancy. And because different organizations approach this multi-cluster situation differently, we do have organizations who has a clear distinction between the dev team and the ops team. For those organizations, the dev team focus only on the code. They don't care about releasing the code. And it is the ops team's job to manage the deployment environment and to actually release the code. And for those organizations, a common pattern would be the ops team will prep prep first the deployment environment. They will create all kind of namespaces for different developer teams. They will start to enforce all kinds of policies. So we encourage the ops team to use the cluster resource placement to do that. And for the dev team, because they only have access to specific namespaces, they will feel more comfortable using the resource placement API to place namespace scoped resources only, deployments, config maps, secrets, etc. So that's why we have those two separate variants. But all those scenarios I've just described, they are not really a hard requirement. You can use the two APIs as in any way you see most appropriate. So those are the two variants about KubeFleet placements APIs. We also offer rollout APIs for safely rolling out changes to member clusters. At this moment, we provide two rollout types, one called the rolling update, the other one called the stage update. Rolling update is kind of, it's very similar to how the standard Kubernetes deployment API handles a rollout. Basically, it tries to upgrade member clusters a few at a time, making sure that at any moment there are only a certain number of deployments, a certain number of member clusters who have available resources. I will dive a little bit deeper into the stage update API. So here's how that API looks like. What this API does is that, as you can see on the screen, it allows developers to group clusters into different stages. For example, I can say some clusters belong to the canary stage, and some cluster belongs to the production stage. What KubeFleet will do is that we'll first roll out changes to the canary clusters, and we'll only proceed to the production clusters when all the changes have been safely applied in the canary stage. The API also allows developers to add time-based or approval-based gated checks between stages. So as you can see on the API, right after the canary stage, KubeFleet will ask developers for an approval before it can move on to the production stage. This gives the dev team a little bit more. This gives the dev team a little bit more opportunity to do, say, additional checkup or kind of validation tasks before rolling out to a greater scale. You can also add time-based gates. On the screen, it shows that after the production stage, KubeFleet will wait for an hour before moving on to the next stage. So that's the stage update API. And the last pillar of the KubeFleet API will be the cluster management API. So in this API, we allow member agent to send heartbeats to the KubeFleet hub cluster, so that the developers can know if a member agent is still working as expected. We will be also exposing all kinds of health check information, so people can learn about whether their API server is still healthy and ready to work using this API. a key feature of the cluster management API will be cluster properties. This is a system that allows platforms like Azure to kind of expose information like CPU per CPU core cost, per gigabytes of memory cost, node counts, CPU and memory capacity, etc. Expose all kinds of platform-specific information on the cluster management API. It gives developers better observability into their multi-cluster system. And KubeFleet also gives people the opportunity to refer to those data when making a scheduling decision. So as I mentioned earlier, you can ask KubeFleet to place workloads only to clusters with the cheapest CPU, with the lowest price of memory, etc. That's the kind of experience we want to provide. Now, so that's the three pillars of the KubeFleet API so far. We have the placement API, we have the rollout API, we have the cluster management API, but we wanted to do more. We are still quite a young project, and we wanted to enable more greater multi-cluster experience. So here are a few topics that we are thinking about at this moment. We really want KubeFleet to not only be able to manage workloads, but also be able to manage the member cluster life cycles, so that we can provide a more like a multi-cluster as a platform kind of a platforming experience. We are thinking about adding descheduling and rebalancing capabilities to KubeFleet. We know that a common scenario our customers have was that they want to move workloads safely from one cluster to another. And they also want the capability to roll back if the new cluster wasn't working at all. So that's the kind of experience we are looking to add at this moment. We also want to add better support for AI workloads. We want to integrate better with the common frameworks people are using, like Argo or Q. We are also planning a number of quality of life improvements. We want to have an API, we want to have a dashboard, etc. So those are the other areas we are looking into at this moment. Yeah, so that's it. Before I'm moving on to the latter half of this presentation, Luke, do you have any questions or concerns or feedbacks about the APIs? Is there anything I can help answer about?
Yeah, that sounds really good, and I do like the concept of being able to essentially pick where the work, like pick where the workloads sit, and then not having to worry too much about like what cluster and where it's located and things like that. I assume I do have a question. It's more of a platform level question. So the KubeFleet APIs are obviously talking to Kubernetes itself. Like, can this run on AKS, or is it?
Yeah, it's you can deploy KubeFleet on any major platforms really. We do most of our development and testing on using AKS clusters, so we actually work
Yeah,
really well with the Azure platform. But technically speaking, you can run it on GKE, on EKS, or on-prem Kubernetes clusters. Really, any standard Kubernetes cluster would work with KubeFleet. Yeah.
awesome, cool, thank you.
Yeah. Thanks so much. Yeah, so in the latter half of this presentation, I will be primarily talking about KubeFleet's performance and scalability. So the situation that we understand that the most, many, if not most organizations, they use something like 10 or 20 clusters in their environment based on the recent CNCF yearly research. But there are exceptions. We have heard from a few customers that they do like to use a lot more clusters in their environment. Some customers they run hundreds of clusters, and they want all of them to get managed. So when we develop KubeFleet, we want to make sure that KubeFleet can handle large scale deployment just as good as a small scale environment. So we really want to ensure that KubeFleet is performant and scalable as much as we can. At this moment, our performance and scalability target was that we want to provide a workable experience when people are using KubeFleet to manage 1,000 member clusters, when they have 1,000 up to 1,000 placements among those clusters. And we also want to make sure that they can run up to 100 concurrent stage updates across all those 1,000 placements over 1,000 member clusters. So that's our performance and scalability goal. To meet this goal, we conduct periodic evaluations to understand our performance and scalability situation. And we also use those evaluations to inform our development, to make all kinds of improvements and bug fixes to help KubeFleet become even more performant and scalable. The most recent round of performance and scalability evaluation was made just a month ago. We call it the 2026 Q1 KubeFleet performance and scalability report. You can actually find that in a blog post of our official documentation. So in this presentation, I will be discussing some of the findings we have so far. So in our rounds of evaluation, we usually follow three steps. The first step being that we first join 1,000 member clusters to the fleet. The goal of this step was to evaluate how much, what kind of performance footprint we will be having when there are only heartbeats traffic in the system. And as one would expect, the heartbeat traffic from member clusters to the hub cluster incurs very limited resource overhead. You can see that when there are 1,000 member clusters in the system, it only takes the hub cluster around less than one CPU core really to process all those requests. The memory usage was about a little bit less than 1.5 gigabytes of memory. And all those member cluster management API objects, they together take around 100 megabytes of space on the etcd backend, which is quite acceptable. I do want to mention that we conducted our evaluation using an Azure cluster. So using an AKS cluster. So the data we mentioned here only applies to the AKS environment. If you deploy KubeFleet on some other system, the profile might become a little bit different. And when there are 1,000 member clusters in the fleet, you can see that the hub agent takes very little effort to process those heartbeats. The CPU usage was less than 100 millicores. The memory usage was something around 200 megabytes. And there's virtually no delay when processing all those heartbeat signals. The average, the P90 delay time was less than 0.1 second. Which is pretty fast. And on the member cluster side, it also takes nominal resources to emit all those heartbeat signals. The member agent CPU usage was less than 10 millicores, and it only uses a little bit more than 30 megabytes of memory. So the footprint is pretty small. And in the second step, we start adding more placements to the system. And for each placement, we will set it up to pick 100 member clusters. And in each placement, we'll set it up so that it places a deployment and a config map around 2 kilobytes of data to the 100 member clusters. And it usually takes KubeFleet around 20 seconds to complete such a placement. Which is not so fast, but it's not really bad, really. Much of this latency is spent on creating bindings and works. Bindings and works are KubeFleet internal APIs. Bindings kind of represents an association between a placement and a cluster. It basically represents that KubeFleet is ready to place resources from a placement to a specific cluster. And works is more like an envelopes of resources. It actually has all the YAML files of the resources to place, so that member agent can read those YAML data from the API and then start applying the resources to the member cluster. Every time KubeFleet picks a cluster for placement, it will create one binding and one or more works, depending on the size of resources, to facilitate this propagation. Honestly speaking, for the placement part, we care less about the latencies because most of the time people don't need to create placements very often. It is not an API that will require a lot of changes. What we do care about is how well KubeFleet will perform when the agent resyncs. As you probably know, KubeFleet is just a collection of Kubernetes controllers. What the controllers do basically is just it reads some data from the Kubernetes API server and it reconciles them. And as with any Kubernetes controllers, not just the KubeFleet, but it applies to all Kubernetes controllers really, to facilitate this kind of read and then reconcile workflow. Every time a controller starts, it must list all the API objects from the API server, and then we'll reconcile all of them. So it's actually quite an expensive process, especially when you have a lot of objects. Earlier we mentioned that for every time KubeFleet selects a cluster for placement, it will create one binding and I guess one work. If we have 1,000 placement, it means that we will be having 100K bindings and 100K works. That means that every time the KubeFleet agent resyncs, it must list all those 100K objects from the API server and reconcile every one of them to make sure that the system is still behaving correctly. This is a process we cannot skip, and it is there by design. And this is as I mentioned, this is a process that's being performed by all Kubernetes clusters, all Kubernetes controllers. It is not just us. So you can probably already guess why we are so concerned about this resync period because it poses significant overhead on the API server and also on the ETC storage backend. It also requires a lot of resources to handle all those API objects on the hub agent side. In adverse conditions, people might experience brief period of irresponsiveness when the environment resyncs. There is also this nightmare scenario where KubeFleet agent starts rethinking, but it crashes in between, and then it reboots. And after it reboots, it must restart all the resync workload from the very beginning, and then will crash again. That kind of thing. It's a really nightmare scenario. The whole system will be stuck in a crash loop. So we'll have to be very careful about that. At this moment, when you have 1,000 placement in the system, it takes KubeFleet around a little bit more than 10 minutes to complete the whole resync process, which means that every once in a while, you might see KubeFleet become a little bit irresponsive, or you might experience a higher level of latency in KubeFleet because the system is busy resyncing all those resources. On the hub agent side, it uses a little bit less than 4 CPU cores and 8 gigabytes of memory during the resync. On the API server side, however, it takes a lot of more resources. Like I mentioned, we use an Azure AKS cluster, and for that AKS cluster, it takes around 13 CPU cores and up to 47 gigabytes of memory to handle a resync period, which is a lot of resources. But Microsoft is paying for that, so I guess it's kind of all right. But still poses a kind of like a high pressure on the system. We feel kind of bad about this, really. And when you have 1,000 placements, all those KubeFleet API objects, they altogether uses around 1.6 gigabytes of space in the storage backend. Now, the tricky part about the etcd storage backend is that unlike a SQL database, its space doesn't scale infinitely. etcd has a notoriously stringent 8 gigabytes space limit per database, which means that when you have 1,000 placement, KubeFleet API objects alone can take roughly 1/4 of the total space. So that's a little bit concerning, which is an area we are trying to optimize at this moment. But the good news is that the resync period has very little impact on the member cluster side. So for the member clusters, they can still there's virtually no side effect at all. All the workloads being placed by KubeFleet will continue working as fine during this resync period. I would also like to mention that the number of existing placements has a little impact on the processing latency of new placements. So if you add one more placement, that's it, the 1001st placement, it will still take around 20 seconds to complete, which is consistent with the processing latency of the very first placement. That's a little bit good news, I guess. At last, the third step we do in the performance and scalability evaluation, we will start running 100 concurrent stage updates. In each update, we'll do 3 stages. Staging, which has 20 clusters, Canary, which has 30 clusters, and there's one last stage called Prod, which has 50 clusters. And we use a concurrency setting of 50%, which means that KubeFleet will, say, for example, in the staging stage, KubeFleet will update 10 clusters in the first attempt, then we'll update another 10 clusters when it finishes. Yeah. So for the latency part, it takes KubeFleet around a little bit more than 1 minute, 1 minute and a half to complete one such stage update. And when we have 100 stage update running concurrently, you can see the latency, as one would expect, would grow a little bit by around 40%. We'll see that each placement will complete within 3 minutes, 2 minutes and 15 seconds to be specific. And during that process, you can see that the hub agent uses a little bit more than 5 CPU cores and a little bit less than 12 gigabytes of memory. On the hub cluster API server end, you will see that the usage was on 8 CPU cores and around a little bit more than 31 gigabytes of memory, which is a little bit high. And this is another area we want to optimize in the coming iterations. The space usage stays at 1.6 gigabytes. Because stage updates won't create many new objects during the workflow. So that's KubeFleet's current performance and scalability profile in a large deployment. What we do want to say from this evaluation is that we do want to mention at this moment KubeFleet can work with large-scale multi-cluster environments. You can have 1,000 member clusters, up to 1,000 member clusters. You can have up to 1,000 placement, and you can run 100 stage updates concurrently. That's only supported. But to make such an environment work, the developers will need to make sure that the KubeFleet Hub agent has sufficient CPU and memory resources. We recommend giving the Hub agent around 8 to 12 CPU cores and 16 to 24 gigabytes of memory, just to be on the safer side. To make it work, we also need the API, the hub cluster API server, and the etcd storage backend to have enough resources as well, so that it can handle the high volume of requests during the racing periods. And we would also recommend that people reserve the KubeFleet hub cluster specifically for KubeFleet. So the recommendation is that for people to not run any workloads on the hub cluster, so that the hub agent can have monopoly of the resources of all those computing capacities on the hub cluster side. And at this moment, we know that the current profile isn't necessarily perfect. We are committed to making more improvements to KubeFleet's performance and scalability. At this moment, we are really focused on revamping our heartbeat and the cluster property collection mechanism to make sure that the heartbeats won't pose much overhead on the system. And all those profiles, as I mentioned, they only really apply to our testing environment. As you deploy KubeFleet differently, your experience might vary too. And if there's any concerns, feedbacks, or if you have any problem using KubeFleet in a large-scale environment, please feel free to reach out to us, and we would be really excited to learn more about the experience.